Okay, hello. I hope this is working. Let me just, yeah, okay. Looks all right. Looks like it's working. So yeah, my name's Ty, and in this video, I'll just be going over the quiz from last year. Uh, yeah, hopefully, like, kind of like an extra explanation of the solutions is helpful. So yeah, I'll be fairly like quick. So I won't like try and like waste time or anything. Yeah, let's get right into it then. So, first question. In week one, we presented a list of four strategies that can be used to manage a risk. Select all the below strategies that are part of that list. I guess I could just go through it and just like say which one sounds like kind of reasonable. Transfer, uh, that's like basically what insurance is. You just like pay someone to take care of your risk. So that sounds like a very reasonable way um, of, I guess, managing a risk. Cry, it does sound, it might be reasonable, but I think we'll say no. I'm not too sure what buying is, but I think because it's quite vague, I think it doesn't really make much sense, like buying what. Assume fetal position. I would argue this is pretty good, but I guess not. Praying. I think it depends if you're like a religious person or not, but let's just assume you're not. So probably not then. Mitigate, like take actions to, I guess, reduce the risk. That naturally makes a lot of sense to manage a risk. Ignore, I think that's not a very good way of doing it. Um, Avoiding the risk is like probably the most basic and straightforward one, is you just don't take that risk, which is very reasonable. And call mom. Um, yeah, I think you could argue this is a good risk management strategy, but really, I think these three options here are the most like practical ways one can manage a risk. So those are our answers. Yeah, pretty straightforward. Okay, in a group of six people, what is the probability that at least two of them have the same zodiac sign? Okay, I'll go over here to do some working out. So this is for 1B. Um, Yeah, so at least two of them have the same zodiac sign. So you can assume that for any given person, all 12 zodiac signs are probable. So I guess we could say that the probability to have like at least two have same, right? That means just like you have at least one pair with like a match. And that's just the opposite of everybody is different. So we can just make this equal to 1 minus the probability all are different. I'm not very good with running with a tablet, but I hope they get better over this recording. So, now I guess like the idea is like kind of working with like at least statements is very difficult, but when we just have it all's different, it becomes pretty easy, right? Um, so what does that look like? So the probability they're all different. I don't actually know what the zodiac signs are, but I know that there's 12 of them. So maybe just like by a month. So like, what does it mean to have everyone different? That means you might have someone from January, someone from February, someone from August, so on and so forth, but they're all different, right? So I guess like for the first person, there are 12 possible months or zodiac signs they can be in. For the second person, there's 11 possible ones they can be in. And then this happens like for six people. So 12, 11, 10, 9, 8, 7. So it's just 12 times all the way through to 7. And then a denominator is the total cases. And that's just like how many possible ways can these six people have zodiac signs? Well, each person has 12 options on what their zodiac sign could be. So it'll just be 12 times 12 times 12, like six times, or just 12 to the power of six. So this is just actually just 1 minus 12p6 over 12 to the power of 6. And it turns out that this is 77.7 2%. Okay, so I'll come over here and I guess you could type it, but we'll just do 77.72 percent. Yeah, cool. So that's like a pretty cool probability question. Um, yeah, go to this next question here. All right, we have Josephine again. Um, oh, this is very irresponsible from her. She's drinking the night before her exam. And not very good behavior from Josephine. But yeah, so her result in a future test is a random variable denoted by X. And she has this YOLO philosophy where she'll consume some random number of Y drinks the night before the test. Okay, we're going to, so this is for question 1C. We'll assume that Y is just equal to 0, 1, 2, 3. Okay, so you can write like 0, 1, 2, 3, with probability just like a quarter for all of them. Okay. Given she consumes Y drinks the night before, her test result is a continuous random variable with this distribution. So we're saying X, given you know what Y is uniform on 10 to 100 minus 2Y. Oh, running out of space here. 100 minus 2Y. That was a bit sketchy, it's all right. All right, what is the standard deviation of Y? Okay, so like a pretty straightforward question. So first of all, we want to find the variance of Y naturally. So the variance of Y is equal to the expectation of Y squared minus like the mean of Y just squared. Okay, to find each of these components, the expectation of Y squared it's just, 1 on 4, because there's a 1 on 4 chance to be everything. 0 squared plus 1 squared plus 2 squared plus 3 squared. And what's that equal to? 1 plus 4 plus 9, 14 divided by 4. And the mean of Y is just equal to a very similar thing, but just the actual numbers now. So 1 on 4, 0 plus 1 plus 2 plus 3. Okay, so 6 over 4. And then so the variance of Y is just equal to 14 on 4 minus 3 on 2 squared. And it turns out that this is 1.25. Okay. Um, and then again, the standard deviation, remember that is just the square root of the variance of Y. So it's just the square root of 1.25, which turns out to be 1.118. Okay, 1.118. I missed a box, unfortunately. Hopefully they still get me the mark. Cool. What is the probability that Josephine scores a HD in that test? Okay, so I think it's kind of maybe reasonable to just kind of consider. So the idea is, right, is that like the way this works is Josephine, she starts off with like Y and then she proceeds to do X. So we can just like consider like what are the possible outcomes of Y and how does that kind of impact how X behaves. So uh, just from before, Y is either 0, 1, 2, 3. Now, let's say she gets 0. Okay. And that means her distribution is 10 to 100 for the test. Okay. Let's say she gets 1. Then her distribution is from 10 to 80. And obviously that doesn't include the HD mark. So then really, and that of course is going to happen for like 2 and 3. So really Josephine has to have 0 drinks for her to get to even be possible to get the HD. Okay. Um, so we can use the law of total probability if we wanted to. We can draw like a tree diagram. Okay. So like this is like y equals 0, y equals 1, y equals 2, y equals 3. And each of these branches have a 1 in 4 chance. Then the probability um, of x being at least 85, okay, for all of these guys, okay. So conditional that Josephine has had 0 drinks, what's the probability that she gets above 85? Okay. So conditional that y equals 0 is going to be from 10 to 100 is her like distribution, okay, of possible values. And from 85 to 100, this is like the sweet spot of the HD. Okay. So this, because it's uniformly distributed, we can just take like lengths of the intervals. So this interval has a length of 15, while the entire interval has a length of 90. So there's a probability of 15 on 90 that this actually occurs. Okay. And then as we discussed earlier, y equals 1, then it's impossible to get x greater than 85. So this is going to be 0, 0, and 0. So the probability that x is greater than 85, okay, unconditionally, we can just apply the law to the probability and just like sum up all of these branches, okay? But only the top branch is non-zero, which is going to be 1 on 4 times, what did I say, 15 on 90, okay? And it turns out this is 4.167%. Cool, that's our answer. It's pretty low HD probability. Hopefully yours is a bit higher. Um, okay. What is the unconditional expected result in this test? So, um, again, there's a couple of ways of doing this question, but I think it's kind of reasonable just to do like the law of total expectation. Um, so if you recall, what that means is the unconditional expectation, so expectation of x, we can just condition I'll take the expectation again of the conditional expectation of x given y. Okay? So we can kind of just ignore the outside and just try and figure out like what the expectation of x given y is. Okay? So that means if I tell you, oh, it's got a lot thicker now. I don't know why I did that. It's quite interesting. Is it back to normal? Okay, that's back to normal. So what this is saying is like, if I tell you what y is, then like, what is x? Well, we know that x given y is uniform on 10 to 100 minus 2y. Okay, so that means just like the expectation of x given y is just the midpoint of 10 and 100 minus 20y. Oh, that was a bit sketchy. So it'll be 100 minus 220y plus 10. Oops. Maybe I might do this. Okay. 100 minus 20y plus 10 divided by 2. Okay. Or if you just like kind of simplify, it's 55 minus 10y. Okay. So I can sub this in, and so I have the expectation of x is equal to the expectation of this thing, which we found is 55 minus 10y. And remember, the linearity of expectations says that I can like take out the constants. Okay. And as we discussed before, the expectation of y is just 1.5, right? So this is going to be equal to 55 minus 10 times 3 on 2, which is just 40. Um, yeah, cool. So the answer is just going to be 40. Yeah, that's it. Um, yeah, hopefully that makes sense. Um, yeah, okay, we'll go to the next question then. That was like a cool question. So we have a sample of size n, where all xi's have the same distribution with some unknown parameter theta. Denote theta hat, an estimator of that unknown theta. In this setting, which of the following quantities is our random variables? Okay, cool. I think like if to answer this question, we gotta just remember that uh I guess hopefully remember that theta hat is like a statistic. It's a function of our sample, right? And because of that, it inherits the randomness of our sample. Okay. So the estimator theta hat is random. That's really important. So that's like the most important part of the question. So I think we could just it's really important in fact that you know that. Okay. That like the estimator itself is random because it's just a statistic. It's a formula of our sample. Now, on top of that, the expected value of a random variable, that is non-random. Okay, that's just like a number. Okay, so um, we just need those facts to kind of answer this question. I think another point I should mention as well is theta random itself. No. Okay. Because we assume that it's just some unknown parameter, theta. Okay. It's unknown. We can't observe it, but it does exist and it's constant. It doesn't change. Okay. So we have to assume that theta is non-random. Okay. And then with that, that should be enough to answer this question. So remember that bias is just the expected value of theta hat minus theta. And this is non-random. This is non-random. So then, okay, bias is not random. Cool. Onto the variance of theta. This is just the expected value of theta hat minus expected value of theta hat squared. And then again, like it's expectation. So variance is non-random. Okay. Theta itself, yep, I agree. It is um non-random. The median of our sample, I think it's like that's like another statistic, right? Like it's another like formula that we can use with our sample. So then as a result, it is again inherently random. Okay. And so yeah, this guy here is going to be a random variable. The median, we discussed the estimator already. The mean squared error. Hopefully remember that the mean squared error can be decomposed into variance of theta hat plus the bias of theta hat squared. And as we discussed earlier, this guy's non-random, this guy's non-random, and so the MSE is going to be non-random. Or even simpler, um, the MSE is just an expectation, which again has to be just a constant, just a number. And then for a similar reason, the maximum is also going to be random because it's a statistic. Cool. Those are our answers. Um, into the next question. Oh, this is a fun question. Complete the sentence by dragging the below keywords where they belong. There's no penalty. Okay. So I guess like this is about hypothesis testing. I hope you can tell. And I don't know how I'm going to answer this question. I might just use arrows. So a blank is a formal rule. I guess like from like grammar. like it's like a noun type thing, like a process. It's like a formal rule. And of these, this is like the only formal rule we like really have the only like formal process. So like a hype test. That's pretty scuffed, but I hope it's like still clear what the selection is. Even when I'm doing this. Um, so is a formal used to something. And I guess like remember when you do a hypothesis test, the whole goal of it, like the whole point of the p-value and the whole point of the statistic is to try and reject a null hypothesis. Okay? So and then you can say here, we have the reject and null hypothesis. So we want to use it to reject a null hypothesis. And then as like a consequence of this, we tend to just like accept an alternate hypothesis, and that's what this is here. So accept. And of course, like we can use process elimination, but it relies on a numeric computation of something, and the only way we know how to, kind of do a hypothesis test is with the p-value, right? The test always involves just computing the p-value. So this last box is just going to be p-value here. Yeah, I hope that is like fairly straightforward. Josephine again, and she's taken a pregnancy test. Okay. And I guess like under the hood, the test is like a hypothesis test. We have this null that she's not pregnant, and this alternate that she is indeed pregnant. Okay, so we're going to assume that Josephine is not pregnant. Okay. In this context, which statements are true? Okay. The test returns pregnant. Okay, so that means we must have rejected H naught and accepted H1. Okay, which is indeed what this first one is here. Um, we we led we had a rejection of H naught and we accepted H1 because the test returned pregnant. Okay, a type 1 error. Recall a type 1 error. I guess I'll write it over here. So a type 1 error means that we reject H naught, but H naught is true. And type 2 is we don't reject H naught, but H naught is false. So what did we do? In this test, as we said earlier, we made a rejection, all right, and we accepted H1, but Josephine is not pregnant, so H naught is true, but we said, oh, H naught is false. We rejected it. So that is literally just a definition of a type 1 error. So this is the correct answer over here. Now, had the p-value of the test been lower, the conclusion of the test would have been the same. Just remember that like with the p-value, that represents like how unlikely or how likely it is for what you observe to occur. So if I see p equals 0.01, that means, oh, what you saw, if you assume the null is true, then what you saw, or anything more extreme, has a 0.01 chance of happening. Okay. Um, and then I guess like from that, if that's too small, if that's too unlikely, you reckon, then you reject. So like a lot of the time it's like, oh, I'd say like 0.01, that's like quite unlikely, so I might reject. But then like what about an even smaller value, like 0.001? Then you go, oh, that's even more unlikely. I'm definitely gonna reject. Right? So like, my point is we always reject for like small p values. So in this test, because we rejected, the p value was already small enough to reject. So if I make it even smaller, naturally I would still reject it because then it's like an even more extreme result, and then I would still want to reject that. So, oh, sorry, it would just be this first one here. Okay, the p-value of a test was larger than the significance level. So if p is less than alpha, we reject. That's like our threshold for what is too unlikely. So then if p is at least alpha, we don't reject. But as we said earlier, we had a rejection in this test. So this is not true. Both a type 1 and type 2 error have been committed. Doesn't really make much sense because as you can see, type 1, type 2 are mutually exclusive. Like one is to reject H naught, the other is to not reject H naught. So we can't really have both. So this is not true. And then naturally, as we've already said, a type 1 error has occurred. A type 2 error can't occur as well. So we can just tick off these last two. They're not correct. And yeah, those are the answers. Okay, we'll move on. All right, let n be at least 2. Let y represent the PV of a regular annuity in arrears payments of 1 for n periods. And let z present the value of an annuity for n periods. Both are computed with the same interest rate. And given this information, which of the following statements are like necessarily true? Okay, and by that we mean that like it's true for all values of n and I. Okay, I like to just try and do this. Maybe just like draw. It always helps for me to like just draw like what each of those are. So we've said Y is a regular annuity. Okay, so it's an arrears payments of 1. So that's just like this bad boy. And then like on a cash flow diagram, it's like 0, 1, 2, n minus 1, n. So for AN, we get $1 at time 1, time 2, time n minus 1, and time n. Okay, for a total of n payments. Let Z be the PV of an annuity due for n periods. Okay, so Z is annuity due, it's just at the start. So A double dot n angle, oops, 0, 1, 2, n minus 1, n. So when do we get payments for this guy? So we get it like straight away, it's like the first payment, right? So we get one here, 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 at n minus 1. And then because it's like you've had 0, 1, 2, n minus 1, that's n payments, right? So then we don't get a payment at time n. So we can see that the difference is basically that like we've had time n. For the annuity, uh, what was it called? A regular annuity. I always get mixed up because like annuity due, it's like kind of confusing like names. An annuity, a regular annuity, we get the payment at time n, right? Because it gets paid at the end of the year. But for an annuity due, the last payment's at time n minus 1. Okay, because it happens at the start of the year. Okay. Okay, cool. So let's just go through each of these questions and just like say whether or not they're right. Okay. Y equals Z1 plus I. Okay. So that's just saying Y, the present value of Y, is just like we get Z and we accumulate it by 1 plus I. Okay. So that's just to say, um, like, remember if we have a cash flow, so if we get a cash flow and we times it by 1 plus I, right? That just corresponds to like moving it ahead by 1 year. Okay. So let's look at Z, right? With Z. On our diagram, the effect of multiplying this by Z is to just move all the cash flows ahead by 1 year. Okay. And as you can see, like if you move this guy ahead by 1 year, it will just go to time 1. If you move this guy ahead by 1 year, it will go to time two. So on and so forth. If you move this guy ahead, then it's at time n. Okay. Um, so yeah, hopefully you can convince yourself that like from the diagram, like this has to be true. Okay. Because we're just compounding everything forward by 1 year. Um, and then like kind of intuitively, like AN, this one, Y, is paid at the end of the year, whereas this guy is paid at the start of the year, right? So then like it's just been like 1 year difference in the payments. So you gotta like accumulate it forward by 1 year. Okay? Cool. Okay. So let's do the next question. Y plus one equals Z. What they're saying is that like if you just like give one extra dollar, so what does that dollar look like on the cash flow diagram? To get $1 just means you just get a dollar at time zero, right? So this new diagram I've drawn here, this is y plus one, and this is z down here, and you can still see that we're just missing a payment at time n, right? Like we made up for this payment at the start, but we're still missing a payment down here, so it's not true. Y plus z is greater than n. It's quite interesting. Uh, it could be true. It could be true. Well, maybe it could be true. But I think just like intuitively, like just take I like to infinity, right? Then that means like the discounting is like really, really strong. So then like a payment in the future of like 1 year is worth like $0. Okay. So then like the annuities are worth like maybe $1 each, right? So then that means if you just like have like a term of like 10 years and the annuities are worth like at most a dollar, like around $1 each, then that's still like less than like N, right? So we have like a counter example for this, and so it can't be true. For y less than z, um, I think it's like let's look at the diagram, right? Uh, like just like intuitively, um, hang on, does that did I make a mistake? No, I think it's okay. Wait, I think I did make a mistake actually. Um, oh no, I didn't. I didn't. Okay, no, I'm good. I'm good. Sorry, I just had like a mind blank. Um, so like, but this question here, y less than z, what does that say? It just means that like the present value of y is less than that of z. Okay. I think it's like kind of true. Like you can just kind of like intuitively just think, oh, you know, would you rather have money now? Because like it's the same number of payments, but Y is just deferred by 1 year. So it's like, would you rather have money now or money later? Like for the same amount of money. And you would just always say money now, right? Because you can just like it's nice to have money now, but you can also just like invest it straight away and just start earning interest on it straight away. So you want to basically just have money now. So as a result, this is true. Okay. Um, moving on, y plus c is less than n. I think we can kind of like do a similar argument as before, but we can just take I to like the limit as I goes to 0 plus. Then that means it's like virtually no interest on your guys, right? On the annuities. So then each payment in the future is like worth like approximately one, like today. Like there's no interest basically. So that means like AN would be um approximately just like N, and a double dot N is approximately N. So then this can't be true, right? Because you sum them up and then they're both N, right? So this is not true. This, however, is looks a bit more convincing. This is only true if we put I equals 0 in, but our condition is that I is non-zero, right? It's still positive. So, as a result, then, like, it's going to be like just below um 2n. Like, really, what the point is saying is that like an have a strict inequality of n. Okay, because there's always going to be some interest, there's going to be some time value of money, but the nominal value of your payments is just n. So this is true. And yeah, that's the question. Cool. This is a very long question one, I gotta say. Um, but yeah, let's move on. Okay, so question 1H. Your bank account earns interest at a nominal yearly rate of 6%, compounded twice a year. And we just got three questions here. So what is the rate of interest you effectively earn on a 3 years period? Okay. That's just saying that like what's the interest rate you get over 3 years? So I guess like on $1. Um so we've said that like oops, sorry about that. That like the nominal yearly rate compounded twice a year, so that's just I2 is 6%. Okay? So that means the effective half annual rate, half year rate, is 3%. We just halve this, okay? So that means on each half year, I get 3%. And now the question's asking for 3 years, which in turn implies like 6 half years, okay? So it's 1.03 to the power of 6. That's how much interest I get. But it just wants a rate of interest, so just minus 1. And it turns out this is 19.4%. You must repay a debt by making a payment of 1,000 in 5 years. What is the present value of this debt? Um, so this is question two. Yeah, I think it's like pretty like straightforward time value of money question. We have 5 years and we have a payment of 1,000 and we're at time 0. And we just want to like bring this guy back to the start of the year. Okay? So that's just discounting it back by 5 years. So just 1,000 divided by 1.03. And of course, this is in years. So the number of half years in 5 years is 10. So to the power of 10. And it turns out this is 744.1. Right now, at time 0, you have 5,000 in your account. You then start to make deposits of 1,000 in the account every 6 months. The first deposit is made 6 months from now. How much money do you have in 10 years right after the last deposit is made? Okay, so what does that mean? So I guess like the way we can look at this is like we have two components. We have like our like upfront investments of oops of 5K. Oh, why is my hello pen? Okay. Let me just rewrite that. It looks super sketch. We have like our upfront investment of 5K. Okay. And in 10 years' time, that's just like 20 half years. So this guy is going to be worth 5,000 times 1.03 to the power of 20. Okay? Like in 10 years' time, from our $5,000, we're gonna have this much money in uh what you call it? 10 years' time. We also have a next component, which is these deposits of 1,000 in the account every 6 months. Okay? And that pardon me, that deposit is going to be made 6 months from now, every 6 months. Okay, so if you picture like our timeline, if we use the unit of like half years, 0, 1, 2, 19, 20 half years, we're going to be doing a deposit, so you see, at time 1, at time 2, at time 19, at time 20. Okay? So to accumulate this guy all the way forward, and we're valuing it at time 20, right? So to bring this guy all the way forward, that's 19 years worth of accumulation. So it'll be like 1,000 times 1.03 to the 19. This guy has 18 years of accumulation. So plus 1,000 times 1.03 to the 18 plus so on. And then this last guy, like you get zero interest on it, you just get paid 1,000. Okay? So then the value of this at time 20, you can just factor out the 1,000, then you have 1 plus 1.03 plus 1.03 to the 19. Oh. And this is like a geometric sequence. So there's the first term is 1. So it's 1 minus 1.03. There's 20 terms. And 1 minus 1.03. Okay. So then, yep, we'll combine these two components. The future value is equal to my handwriting is quite messy. Is this investment component? So that's just 5,000 times 1.03 to the 20 plus the value of all our deposits. Okay, so 1,000 times 1 minus 1.03 to the 20 over 1 minus 1.03. And it turns out that this is 35.9 thousand dollars. Okay. I just chuck that in there. Cool. All right. All right, question 2 now. That's a long question. All right. All right, on to like some stats now. Following a natural disaster, the time T it takes in years for a given policyholder to lodge a claim is a continuous and positive random variable T, which has this CDF given by this formula. And it gives an example of how CDF works, which I guess I hope you know. Anyway, which of the correct expressions are for calculating expectation of T squared? So just remember that like in general, if you want to find the expected value of like a function of a random variable, it's just the integral over the entire domain of that function times the PDF dx. Okay, so as a result, it feels natural just to try find out what the PDF is because we're given the CDF but not the PDF. So remember that the PDF is equal to the derivative of the CDF. I've been using T, using X. I'll just change the T to keep with the question. So D on dt, FT, or just D on dt, e to the minus 1 on T. And like this guy here, that's just like minus 1 on T squared times minus 1. So just 1 on T squared, e to the minus 1 on T. Okay, cool. So now we can just figure out what e to the T squared is, expectation of T squared. It's just going to be integral from 0 to infinity, because that's like what it's defined over. T squared, because that's just our function, times the PDF. So 1 on T squared, e to the minus 1 on T dt. Oh, just simplifying this, e to the minus 1 on T dt. So it's not this one. Don't get tricked by the domain. I guess it's this guy right here. That's our answer. Compute the probability T is less than or equal to 5, given T is at least 4. Okay, so to be 1, the probability that t is less than equal to 5, given t is at least 4. Just like by the definition of this probability, it's just the probability of t less than equal to 5 and t is at least 4 over the probability t is at least 4. And then like t less than equal to 5 and t at least 4, that's just the probability. T is just like between 4 and 5. Okay, cool. And now I can kind of like simplify this out. So to evaluate this, this is just a probability that t is less than equal to 5, but I don't want to include all the events when t is less than 4. So minus the probability that t is less than 4. Oops, daisies. Oh. All over, and then probability t is at least 4. Just 1 minus probability is t less than or equal to 4, the complement. Okay, and we want to get it in terms of less than or equal to because we've been given the CDF up here. Okay, so then this is going to be e to the minus 1 on 5 minus e to the minus 1 over 4 over 1 minus e to the minus 1 on 4, which in turn is equal to 0.18052. Oh, but I get answers to the questions in this box. Oh, okay, so you have to like do it. I guess like I'm just doing it on the page then. Yeah, I guess you could just write that looking out in there. The probability obtained above should be different to the probability t is less than or equal to 1. Explain in context what the above probability represents. Also provides a real-world reason explaining its difference to the probability t is less than or equal to 1. This is actually like a really interesting question. But like the idea is that like I guess like what the question's trying to hint at is saying, oh, it's like saying t is already at least 4, right? Um, then like t speak for like, so let's say put it this way. I tell you t is at least 4, okay? And then I ask you, okay, then given this, what's the probability that t is just less than or equal to 5? Okay? So that's like a difference of 1. So a naive answer might be go, oh, this has a difference of 1. Oops. Why? This is the shoddiest like tablet ever. It's like really being so annoying. So this has like a difference of 1. So I might say, oh, this is just equal to this, right? The probability t is equal to 1. Okay. But it turns out that this is not the case. Okay. Um, so explaining context what the above probability represents, it means that conditional that for time has already passed. Did it give a unit? 4 weeks has already passed. Then you have to wait like even you have to wait like just 1 more minute, right? Past 4 minutes. And that's different because like at the very start when we had t is less than or equal to 1, it's like no time has passed yet. Okay. Um, so uh I guess like in the context of this question, I should probably read this. So it's like following a natural disaster, the time T it takes in weeks for a policyholder to lodge a claim is this distribution. Okay. So why does it make sense? So this is saying given 4 weeks has passed since the natural disaster, what's the probability that like they then make a claim uh, within the next year, i.e., before t becomes greater than 5. Um, why 7 to t equals less than 1? Well, I think that like right after a natural disaster, it's you probably like claim like within the first week, right? Like it doesn't really make sense for someone to like wait 4 weeks and then make a claim. right? So it's quite reasonable to just like assume that after 4 weeks, they're probably not gonna make a claim, right? Because they just like haven't really like you know really experienced anything they need to claim. And most of the density would just lie within like the first week. Okay. It doesn't really make sense just to like kind of just wait to make a claim and just like kind of it's just kind of strange, right? I think just people make claims straight away. I think a different example as well could this like with respect to time could be like maybe the time until the machine breaks. Okay. Like let's say a machine has been operating for 20 years, then the probability that's going to break within the next year, I would say that's a lot higher than the probability it just breaks within the first year when it's brand new. You know what I mean? So this is kind of showing that like it might be a bit, it seems unintuitive, but yeah, like conditional on time passing, our distribution can really change. Okay? Hopefully that explanation made sense and it wasn't just a ramble. Uh, I hope. Okay, so do this. Assume that T1 to T5 are the time taken by five policyholders to lodge their separate claims. Okay, where the CDF is done as so, and in the question as well, it also said, I think it says we can assume it's independent somewhere. Independent policyholders to lodge their separate claims. What is the probability that out of five policyholders, at most one takes longer than 1 week to lodge a claim? Okay, so let's let n be equal to the number of policyholders that like lodged a claim longer than one. It took like more than 1 week to lodge a claim. Okay. Um, then because they're all independent, they all have their own like individual probability of I guess like uh, lodging a claim right past 1 week. So first of all, I should probably say the probability of lodging a claim after 1 week. That's like one minus probability. You just lodge the claim within the week, which is one minus e to the minus one, basically, like minus 1/1, just from the CDF here. Okay, so if each policyholder has this probability of taking longer than 1 week to lodge a claim, that means they just all have that. And the number of people that take more than 1 week is just binomially distributed. There's five policyholders, and the probability of each guy is 1 minus e to the minus 1. And we're asked to find the probability that out of five policyholders, at most one takes it. So that's just the probability n is less than equal to 1, which is the probability that n is equal to 0 plus the probability that n is equal to 1. Okay. From this, like, what's the probability that n is equal to 0? That's just like 1 minus e to the minus 1 to the power of 5. So that's just e to the minus 1 to the power of 5 plus the probability n equals 1. So that's going to be 5 choose 1. And then the probability one of them is 1 minus e to the minus 1, just once. And then e minus 1 to the power of 4. And it turns out that this is 0.0646. And that's our answer. So yeah, cool question. Okay. Having sold her car because she was too risky driver, Josephine again, now hitchhikes to go places. Okay, you can say she traded one risk for another. At the moment she arrives at a hitchhiking spot, somebody picks her up, expressed in minutes, follows an exponential distribution. We could just say all the times until it gets picked up are independent random variables. Okay, so she hitchhikes once per week for 9 weeks, and she gets 9 observations. Okay, so it sounds reasonable to try and find an estimator for beta. Okay, so we're working with the exponential distribution. if you go to our common distributions and under the continuous one, exponential beta is as so. And we're trying to figure out an estimator for beta. Okay. Always like a reasonable approach is to just go, oh, the mean of the distributions equal to one on beta. But remember that like the sample mean uh tends to be a very good approximator for the actual underlying um mean itself. So then, as a result, it's kind of reasonable to assume that like the sample mean is a good approximation for just 1 over beta. Okay. And so as a result, we can say that our estimator is just going to be 1 over x bar. Okay. I.e. the reciprocal of the sample mean. Okay. I think like a justification, as I set out loud just then, is it was just saying that like, oh, the sample mean is approximately the expectation, and because of that, we can just kind of jump. Uh, hello, we can kind of just jump straight to this, and then the estimator kind of just follows through, like quite naturally. Okay, the total time it took for Josephine to be picked up on 9 separate occasions is 155 minutes. This information uses information to conduct a statistical test where we have this at our hypothesis. So let's write this down on our page. So H naught is that beta equals 0.1. H1 is that beta is less than 0.1. Use alpha equals 1%. At minimum, you must provide a p-value and clearly state the conclusion of your test as well as the logic behind it. So, how you go about it. Okay, we can also assume the sum of 9 independent exponential random variables follows the normal distribution, which is going to be very useful, I guess. So, as our test goes, we need to first identify a statistic, and I think that the saying that we can use the sum of the 9 independent exponential random variables, uh, it sounds quite reasonable to just say, yeah, okay, that's going to be our test statistic. So, let's let uh, our test statistic t be equal to the sum um of all of these guys. Okay. Um, be like our test statistic. Okay. Um, and then like what we're saying as well is that I guess like as like a side note, like would we reject for small or large values of test statistic? So to say that beta is less than 0.1, because the mean is 1 on beta, the smaller beta is, the bigger the expected value is, right? So if I want to accept H1, I want to see like big values of my statistic. Because like if we assume beta equals 0.1, that means on average it takes Josephine 10 minutes to get picked up. So that means I expected this to be like 90. And so I want to see very big values, like values above 90, to be able to reject and accept. And indeed, we see 155. So this might be big enough. So let's test this out. So we can assume from the hint that t is like some normal distribution. Okay. And we always just use the mean and variance as our parameters. Okay. So it's going to have mean of just expected value of t and variance just the variance of t. Okay. Um, and I can assume as well that this is just like under H naught. Okay, so we're assuming H naught is true and that beta equals 0.1. Okay, so then as a result, the expected value of t is just equal to by linearity, the sum from I equals 1 n expectation of xi, and assuming beta equals 0.1, each of these guys has a mean of 10, and so this is equal to 90. Okay. The variance of t, that's equal to again, we can do linearity because it's independent. 1 on 9, the variance of xi. And if we come over here, it's 1 over beta squared. Okay. So then like that means the variance of each of these guys is 1 over 0.1 squared is 100. And so this is 9 times 100 is 900. Okay. Cool. Okay. So we had the distribution of our test statistic. Now it's time to figure out the p-value. So our p-value is just the probability that t exceeds our observed statistics. Because remember, we're rejecting for big values of t, so we want to reject for the upper tail. That t is at least what we observed, 155. And as before, it's assuming H naught. Because if we assume H naught, then we know the distribution has mean 90 and variance 900. Okay? So, I can do my standardization trick. So the probability, Z is at least 155 minus the mean was 90 over the square root of variance, so the square root of 900. Okay. And this is equal to 1 minus like the CDF of a standard normal evaluated at 2.17. So this is like the z-score. If I go to my z-score table down here, go 2.17, 0.985. So I'll do 1 minus 0.985 equals 0.015. But over here, I said that the significance is 1%, and this is greater than 0.01, which is our alpha value. So as a result, we do not reject H naught. Okay? And that's the question. So a pretty standard hypothesis test. And yeah, hopefully that was helpful. Okay. Okay, so just for this question, I think let's make this question a little bit better. So I guess I'll read the question now. So Sachi is a new retiree with 500 grand in his bank account. The effective interest rate he earns on that account is 6% per year. And like it's a bit conflicting because it's effective per year, compounded monthly. I think just ignore this. Because all we need to know is that the effective interest rate on the account is 6% per year. To fund his retirement, he will withdraw from his account monthly amounts of R in advance over a 20-year period. So there's 12 times 20 withdrawals in total. Once withdrawn, those amounts are considered gone. He spends that money because life is for living after all. The account is emptied after the last withdrawal. Okay. Whoa, what's my pen doing? So, um, what is R? So, the idea is basically is that R just has to basically add up in present value to 500,000 bucks. Okay. We're told that they do the withdrawals in advance, so the first withdrawal happens immediately. So it's going to be R times A double dot, because A double dot means it's not at the start of the year. Okay. And because it's done in months, we're going to be doing 240 total withdrawals, but it's not at this 6% rate. It's at like some monthly rate. So I'll just do like an at like J. Okay. So this is the present value of all his withdrawals, and the amount of money that he actually has is just 500,000 bucks. Okay, that's basically it. Cool. So once withdrawn, I mean, sorry, not that bit. Talking about how it's in monthly. Okay. So to do that, because we're going to be using the monthly, we need the monthly effective interest rate. Okay. So what does that mean? The monthly effective interest rate, so 1 plus J, this represents how much interest we're going to be getting in 1 month. Okay. And all we have is 6%. So we know in 1 year we get 1.06 worth of interest. And for this to be equal, we just need 12 months. So this to the power of 12 will be equal to this. And you can just see that if we rearrange this, J is just equal to 1.06 to the 1 on 12 minus 1, and it turns out to be 0.487%. Okay, so now we can solve for R. So we have R is equal to 500,000 over, and remember A double dot 240 is just like accumulated forward A. So 1 plus J A 240 with no dots. A 240 at J. Okay. And this is equal uh yeah, and then now just do the formula. So 500,000 uh 1 plus J times 1 minus 1 plus J to the minus 240 over J, just like doing our annuity formula. And if you sub this in, you get 3519.33. So that's what R is. Over the entire 20-year period cover which Sachi withdraws, how much interest will you have earned in total? So that you can just do this is just think, okay, like what actually is R? Like R is like what our payments are, and the interest is just like the kind of like the extra money that we got. So really, because Sachi does 240 payments of R, right? That's like how much withdrawal Sachi gets. So how much money in this period he gets to really enjoy. Okay. Um, but really he only started off with an investment of $500,000. Okay. So just this difference is going to be like how much interest he gets. So how much money Sachi got to enjoy minus the upfront investment. Okay. And then if you sub this in, you get 3, 4, 4, 6, 3, 9. And yeah, that's I think that's the entire quiz. So I hope you found that useful. Yeah, thank you for watching.